That's just a little cueing thing at the very beginning of each segment. Yeah. Okay, so here we are moving on now. We've talked about degree measure and radian measure and 16 critical angles. So what I want to begin before we get to the sector area and circular motion topic, what I want to make sure we do is have a better means of measuring angles accurately with more precision than just saying it's, say, 5 degrees or something like that. Okay? And we also want to know how to convert from radian measure to degree measure easily. Okay? So we want to be able to, first of all, probably convert from degree measure to radian measure, or the other way around. The other way around. Now, you've all converted units before. Like you might have converted miles per hour into feet per second. You might have converted gallons of something into quarts, or maybe even over into the international system of measure into gallons into liters. Okay? So we want to be able to convert between two ways of measuring angles. So our conversion factor is the following. We know that pi radians is equivalent to, I'm going to treat it like a fraction, like a ratio, is equivalent to 180 degrees. And so that is equal to precisely 1 as a conversion factor. No different than you measure, maybe picking up a map and looking at a map, and you look at the scale on the map and you go 1 inch equals 500 miles. And then you can just measure off on your map, say 5 inches, and 5 times 500 would be 2,500 miles on your map. So you've been doing that sort of conversion all along, ever since you were a kid probably. So this ratio is a conversion factor equivalent to 1. So let's say I took one of our angles. Let's say I took 5 pi over 6 radians, and I was interested in how many degrees that is. Now, the way I convert units is I always do it this way. And if you're taking a chemistry class and you're doing something where you're converting units, or some other biology course or whatever, this is the way that I usually convert units. I start out with what I want over here, and here's what I'm starting with, my given information. This is the given. Now, to convert from radian measure, which is given and known, into degrees, all I have to do is multiply the given piece of information times the conversion factor. And I know that 180 degrees, if I turn this fraction upside down, 180 degrees is equivalent to pi radians. So this is my conversion factor that I tag on here as a multiplier to the given information. And now you notice in the numerator there's radians here, 5 pi over 6 radians. So radians reduce with radians. And notice also that pi reduces out. 6 divides into 180, we know 30 times. 30 times 5 is 150. So there you go. 5 pi over 6 radians is now equal to what we wanted, 150 degrees. You can do that in reverse, obviously. If you were given something in degree measure, you'd multiply it by the conversion factor upside down, where it would be pi radians equivalent to 180, and you'd reduce that. Okay. Right? I am very curious, and I think you might be too, back when I told the story about the wet noodle for radian measure to create 1 radian, right? I'm very curious about how many degrees is equivalent to 1 radian. Now, let's back over here to the other board for just a second. Back to where we talked about the definition of a radian. And the fact that when we went all the way around, we didn't quite, with 6 of them, we didn't quite get all the way around, did we? 6 radiuses on the arc, we didn't quite get all the way around. So, but if I took 60 degrees How many 60 degrees are there to get to 360? Exactly all the way around. There's 6 of them, right? 6 times 60. So that means then that 60 degrees is actually a little larger than 1 radian of angle measure, isn't it? Doesn't that indicate, based on that story I told earlier? So 60 degrees should be just a little bigger than 1 radian. In other words, 1 radian should be a little less than 60 degrees. If you think about the fraction, the way that we sort of told that story earlier. So let's come over here and just do the math. So here we have 1 radian, and I need to multiply that by my conversion factor, 180 degrees over pi radians. And if I turn on a calculator now, and let me go over and grab the calculator. And I'm back on my home screen, and so all I'm going to do is I'm going to punch 180 and I'm going to divide it by the pi character, and I get 57.29 degrees. Approximately 57.3 degrees. So that might be a handy thing for you to kind of have in the back of your mind, that if you ever see 1 radian popping up, that you know that it's a little less than 60 degrees. Okay? Now let's say you were measuring, let's say you're a surveyor, or you're an astronomer. Then you are typically measuring with great accuracy. You need to be able to measure angles with great accuracy, don't you? If you're an astronomer pointing a telescope, whether that be a visual telescope or a radio telescope, something like that, then you need to be able to elevate. You need to be able to elevate very accurately to find a star or something out in the universe, very accurately elevate, and then rotate to be able to point in a certain direction. Make sense? Okay, if you're a surveyor, you need to be able to have a measurement in a certain direction to a point that might be really far away. Now, what if you were just off by a microscopic amount of a degree? Couldn't you be quite a ways off out there in the distance on that arc and miss the spot you should be getting at if you're slightly off? So we need a very accurate way of measuring angles. And so what we do, we use the same vocabulary that we do telling time. We have hours. We don't use that word though, but we do use the word minutes and seconds to break down the measurement of time. Okay? So what we do is we will take and write something like this. We'll say something like 35 degrees, 15 minutes. And we put a little tick mark to indicate minutes of measure. So here's our symbol for degrees. Here's a symbol for minutes. Now, what in the world is a minute of angle? 60 minutes equal 1 degree. So 15 minutes is equivalent to 1/4 of a degree, just like 15 minutes of an hour is 1/4 of an hour. Okay? Got it? So this is equivalent to precisely 35.25 decimal degrees. So this is one way of writing it. 35 degrees, 15 minutes. It's exactly equivalent to 35.25 degrees, precisely. Everybody all right with that? Okay. That accuracy to the nearest minute is still not good enough for astronomy or surveying. We need even more accuracy. So what we do is we tack on another conversion factor, that there are 60 what are called seconds in 1 minute of angle. 60 seconds. Okay, now here's an example. 35 degrees, 15 minutes, and 30 seconds. This is the way you'll see this stuff written. and this indicates seconds of angle. So notice the conversion factor back here. There's 60 seconds in a minute. There's 60 minutes in a degree. And so in 1 degree, there are 3,600 seconds. Just like in an hour of time, there are 3,600 seconds in an hour. And if you're in good physical condition, resting, most people, a person in good physical condition, their heart rate might be around 60 beats per minute, and that's going to be right around 3,600 heartbeats per hour. Okay? Can you remember that? Just like telling time, or very similar to telling time. So now, let's convert this. This is called DMS measure, degree, minutes, and seconds measure. And let's convert this to decimal degrees. Decimal degrees. So here's how we do that, and I'm going to erase a little spot on the board. Any questions so far? Any confusion? Okay, I want to make sure you guys, folks, are with me as we move through this stuff. Okay. So we've got some new conversion factors. So a degree is equivalent to 60 minutes. Similarly, 1 minute is considered is equivalent to 60 seconds, and there's 1 degree is equivalent to then 3,600 seconds. Okay, so now we have an example we're working on. And this is good enough for orienting a telescope or a surveying instrument for very, very accurate measurement. Okay. So what we want to do is try changing from DMS to decimal degree measure. So the best way to do this is simple arithmetic. 35 degrees plus 15 minutes. Make it an addition problem. I'm not done yet. Obviously, I don't have the seconds on here yet. Now, I want to convert this minutes into degrees. I want to convert this minutes, 15 minutes, into degrees. So I tag on a conversion factor. 1 degree is equivalent to 60 minutes. You can see that the minute units disappear, they reduce out, and we're left with 1/4 of a degree there, aren't we? See that? 15/60 is 1/4. Feel good? Okay. Plus, don't forget we have 30 seconds to deal with. Let's convert the seconds into degree measure. And so we know in 1 degree, there are 3,600 seconds. The second units reduce out, and we're left with 36 hundredths of a degree, right? Very small number. Okay, so we will then turn our calculator on and add these 3 numbers together. This one plus that one plus that fraction. And we're going to get 35.2. Anybody done it yet? 583. How far do we go?
333.
Oh, keep on going, huh? Okay. Now, how far should we write down? If I gave you an original angle, 35 degrees, 15 minutes, 30 seconds, how much accuracy, how many decimal places should I write down to make sure that I've captured that 1 second of angle accuracy? Right? 1 second of accuracy. So let's do the following. Let's ask how many degrees, here's what I want, is equivalent to 1 second of angle. 1 second of angle. Okay? I'm just converting units. So I'm going to tag on here the fact that 1 degree is equivalent to 3,600 seconds. And so what I'm going to do then, my units of seconds disappear. And so if I take the reciprocal of 3,600, I will get an approximate reading for 1 second of angle. And that turns out to be 0.00, somebody want to punch it? 1 over 3,600? much? What's the number?
2.7.
In scientific notation, what's it say?
2.77, 10 to the negative 4.
10 to the negative 4. Like that, right? So look at what this is telling us. That if we write down an angle such as this one up here, 35.25833, how far do we have to go? If we round it off here around the 4th decimal place, we're going to be carrying the accuracy good enough for surveying or astronomy work. Okay? So we want to go to that 4th decimal place probably if we're going to do that much accuracy in our measurement. Okay? 35.2583 degrees will be pretty darn close to the original measurement in DMS measurement. Okay, so that's how you do it. That's how you convert from degrees to radians or back the other way, and that's how you take something in degree, minutes, and seconds measurement and kick it over into decimal degrees. Okay, let's talk about sectors of a circle now. Sectors of a circle and the amount of area that might be there. And I'm going to come back over to this board. So let's see. Let's start with something we know. Here's a circle. We know that the area of a circle is equal to, all together now? Pi r squared. Very good. Okay. Better know that. Okay. That would be a whole circle, right? Underneath here, I'm going to draw a subscript for indicating a whole circle. Okay. Let's see. If I did just half a circle, area of half a circle, I'd take half of this, wouldn't I? Right? Everybody knows pi r squared. If I took half of that area, I'd have the upper half, say, or the bottom half of the circle, or the right half or left half. Okay. What if I did a quarter of a circle? What am I doing? I'm trying to look for a pattern here. Trying to look for a pattern. So that if I talk about something other than a nice half a circle or a quarter of a circle, right? If I'm talking about just some slice of cake or something, I'll be able to tell what the area is, and I'm looking for a pattern here. So if I took half of this, I'd have pi over 4 r squared. So what happens? Everybody with me? Simple arithmetic so far? What happens if I've got a sector of a circle where I know the central angle, theta, and I know some radius? What's that area? What's that area? Let's see. If I was doing this quarter circle, I know that that angle is pi over 2, right? But my formula for the area says that it is, this thing right here is half of that pi over 2. Look up here at the whole circle. If I took the whole circle, I know that my angle all the way to do the entire rotation is 2 pi, and I see that this is half of that angle, isn't it, in my formula? So if I'm on a sector of a circle, then doesn't it make sense that it looks to me like it's going to have the area of some theta sector of a circle a theta sector of a circle's area would be what portion of theta? Half. Doesn't it look like half of theta times r squared? So you don't have to memorize this thing. All you've got to do is come back and think of this fundamental shape that you're familiar with from pre-algebra days, And think about the fact that the central angle, you're talking just simply half of the central angle is sitting right here, right? Half of the central angle. For the half circle, here's your central angle pi, half of that is the area of that sector, etc. So there's a formula that you see in the textbook for the area of a sector of a circle. It's that easy. To use the formula, though, how do you measure this angle? Revolution measure, degree measure, or radian measure? You have to use radian measure on that. Must be radian measure. Not too tough. Radian measure. So, I think we need a little practice. Because I can sit here, I can go on for hours doing stuff like I've been doing with you, but I don't know if that's getting into your brain or not. So what I need to do is to stop for a second here, give you something, have you do a calculation, and see if you get the right answer. So let's say we just had the holidays. So let's say we had a nice big old apple pie sitting there. And since you're taking math classes and now taking trigonometry, let's say you decide to cut yourself a 75-degree slice of that apple pie. And the radius of the pie, let's say you've got a 6-inch radius pie. Okay? So I've got a radius of 6 inches, and I'm taking a 75-degree sector of that pie. Now, what I mentioned earlier today is I always want you to draw a sketch. Always draw a sketch, if at all possible, with the given information. So if I take and draw myself a 6-inch radius sector and I go for a 75-degree angle. Now that's a pretty big angle. That's more than a radian of rotation. I'm going to have something that's going to look like that, where that angle is 75 degrees. And what I'm interested in is how many square inches of pie do I have? In other words, I'm wondering about what that area is. Okay, let's go ahead and do it. How many square inches of pie do you get to eat? If you're watching the recording, what I'd suggest you do is you pause the DVD or the recording right now and go ahead and work this problem out, and then hit play or fast forward and see if you got it right or not.
The radius was 6 inches.
So while you folks are penciling that out, I'm going to go ahead and just write the solution up here. what I ended up getting was 23.56 square inches of apple pie. Yes, Brooke?
I got confused where the pi over 80 came from.
Where what?
Where the pi over 80 came from.
Pi over 180
Yeah.
came from?
Over 180.
See, the problem I gave you here, I said 75 degrees. Here's the formula. Area equals 1/2 radius squared times theta, and that's equal to 1/2 of 6 squared times 75 degrees. But you can't use degree measure. You have to convert that into radian measure. So we pop this in, and we get this when you do the calculation. Now, if you think about, what if you built yourself a square that was 6 inches square? This sector is inside that, right? This sector is inside that 6-inch square. So that 6-inch squares area would be 36. So you better get an answer that's less than 36 to give you a rough feeling for this. And that answer is right in the ballpark. Okay. The thing I did not get to today, because I took my time on all this material, is I did not get to circular motion. So what we'll have to do is we'll have to begin the next session with circular motion, which is going to take a little while. But please get going on that first homework assignment between now and the next session. Okay? We're out of time.